Now we're going to look at Archimedes principle. Archimedes principle. I'm going to state it first and then we'll prove it. Archimedes principle says that an object immersed in a fluid is acted upon by an upward force equal to the weight of the displaced fluid. So let's say this is a fluid over here. You've got this object over here. This law says that there will be an upward force that we call buoyant force exerted by the fluid on the object, which is equal to the weight of the displaced fluid. In other words, which is equal to the weight of the fluid of the same volume as the object. Okay, so let's say that this principle says that an object immersed in a fluid is acted upon by an upward force, let's say called buoyant force, equal to the weight of the displaced fluid, Okay, so when an object is immersed in a fluid, there will be a force exerted by the fluid which is equal to the weight of the fluid of the same volume as the object, or to the weight of the displaced fluid. So what's the origin of the force? This force is the force due to pressure difference at the top and at the bottom. The cause of the buoyant force is the pressure difference between the top and the bottom, or between the bottom and the top. So now we're going to assume the shape of the immersed object is in a cylindrical shape. So we got this fluid over here, and then this is an immersed object over here. So let rho f be density of the fluid, and let rho naught be density of the immersed object, Okay, so the cause of the buoyant force is the difference between this upward force, that's due to the pressure over here, and the downward force at the top, that's due to the pressure over here. So this buoyant force, that's the force exerted by the fluid, okay, equals this force over here. Let's say the pressure over here is P, the pressure over here is P naught, that's pressure at lower level, this is pressure at upper level, and the force is pressure times area. So this force equals this buoyant force equals the force exerted at the bottom, which is P times A, where A is the cross-sectional area of the cylinder, and let's say the height is h over here, okay, minus the pressure, the force at the top. Okay, so this gives you P minus P naught, the difference between the pressures, times cross-sectional area. This is the buoyant force. But remember this formula: pressure at the top equals, pressure at the bottom equals pressure at the top plus density times gravity times height, okay? Or P minus P naught, the difference in the pressures equals density times gravity times height, right? So if you put that over there, you get the following. The buoyant force equals density times gravity times height times the cross-sectional area. Okay, now remember, this is the density of the fluid, I should say. This is the density of the fluid. It's the density of the fluid. All right. Now we have the density of the fluid times gravity times h times a. What does this represent? This is the height of the immersed object times the cross-sectional area. That is the volume of the object. So, but h times a, that's height times area, equals v naught, which is volume of the immersed object, Okay, so we have the following. The buoyant force equals density of the fluid times the volume of the object times gravity. Okay, so what do you have? We have the density of the volume, the density of the fluid, but the volume of the object. Okay, so this is the weight of the fluid of the same volume as the object. Okay, so this is weight of the fluid with the same volume as the object. That is Archimedes principle, with the same volume as the object. Okay, so Archimedes principle says that the immersed object will be acted upon by a buoyant force which is equal to the weight of the displaced fluid, or to the weight of the fluid with the same volume as the object. Okay, now let's look at weight in a fluid. Weight in a fluid. Now, an object will weigh less in a fluid than it does in air because of this force, because this force is opposing the force of gravity. Okay, so let's use weight fluid for this one. Okay, so what do we have over here? You got this immersed object over here. There are two forces acting on it. You've got gravity pulling down, let's call this weight in air, but then the fluid is also exerting an upward force B. Okay, so the weight in a fluid is the difference between these two forces. Okay, so we can say that the weight in a fluid, the weight inside a fluid equals the weight in air minus the buoyant force. Okay, what's the weight in air? As we know, it is the mass of the object times gravity. That's the weight of the immersed object in air. Okay, and what's the mass? It is the density of the object times the volume of the object times gravity. Okay, and we saw that the buoyant force is the density of the fluid, but the volume of the object times gravity. Okay, so it follows that the weight in a fluid is the weight in air, rho naught B naught G, minus the buoyant force, which is the density of the fluid, V naught times gravity. Okay, so this is a formula for the weight in a fluid. Or you can factor out this V naught G over here. So you can also say W fluid equals, if you factor out this expression over here, and then we've got the difference between the density of the object and the density of the fluid. Okay, so you can say that either it is weight in air minus buoyant force, or is the difference between the density times the volume of the object times gravity. All right, so that's how you calculate the the weight in a fluid. An object would weigh less in a fluid because of the buoyant force. All right. Okay. Example. Let's say an object of volume, let's say 400 cubic centimeter, and density, let's say maybe 3000 kilogram per meter cubed, is immersed, let's say in water. The density in water is 1000, let's say density 1000 kilogram per meter cubed. Okay, so let's ask some questions. A, calculate the force exerted by the fluid on the object. Okay, this is force due to pressure difference, in other words the buoyant force. So that's what we're looking at. We want to calculate the buoyant force. So what do we know? The volume is 400 cubic centimeters. Okay, and then the density of the object is 3000 kilogram per meter cubed, and the density of the fluid, which is water, is 1000 kilogram per meter cubed. Okay, that's the density of the volume. Now, if you remember, meter cubed is a million times centimeter cubed. Okay, so that means centimeter cube is 10 to the power of -6 meter cubed. Okay, all right, so because of that, V naught would be 400 times 10 to the power of -6 meter cubed. Okay, in other words, it's 4 times 10 to the power of -4 meter cubed. We have to use the SI system to do the calculation. All right, so the buoyant force, as we saw before, is the density of the fluid, the volume of the object, times gravity. Okay, so the density of the fluid is 1000, the volume is 4 times 10 to the power of -4 meter cubed, and then gravity is approximately 10 or 9.8. Okay, so this is 4,000 for, it's basically just 4 newtons. Okay, so this is the force exerted by the fluid on the object. Okay, and then let's see, calculate the weight of the object when fully immersed in water. Okay, so this is the weight in air minus the buoyant force. So we're looking for the weight in a fluid. All right, and we have obtained an expression for that over here. It is the difference between the densities times the volume of the object times gravity. Okay, so this one is V naught G times the difference between the densities. All right, so the volume of the object is 4 times 10 to the power of -4 meter cubed. Gravitational acceleration is approximately 10, and then you've got the density of the object 3000 minus the density of the fluid 1000. Okay, and that is 2000, 20,000. That's going to be 8. Well, 3000 times 1000 is 2, so that is 8 newtons. Okay. All right. Now we're going to look at floating objects. Floating objects. Okay. Now let's say we have an object partially immersed in a fluid. Let's say this is the fluid, and then we have this object partially floating, partially immersed in a fluid. Okay, so let the total volume be V naught and the immersed volume be Vi. Okay, so this is a fluid, so you've got V naught is volume of object, Vi is immersed volume, and of course we're going to use rho f for density of fluid, and then rho naught density of object. Okay, density of the floating object. Okay, now obviously this object is at rest. So this object is at rest, the net force acting on it is 0. Okay, so since it is at rest, the net force acting on it is 0. The net force acting on it is 0. So that means the forces acting on it are balancing each other. What are the forces? We have gravity pulling down, that's weight in air, the weight, and then you've got buoyant force pushing up. These two forces are balancing each other. That's why the object is at rest, because these two forces are balancing each other. Okay, so that tells you the weight in air and the buoyant force are balancing each other. That's why it's at rest. All right, so this implies the weight in air, which is pulling down, equals the buoyant force. Okay, now the weight in air is the mass of the object times gravity. Okay, and the mass is the volume of the object times the density of the object times gravitational acceleration. Okay, and the buoyant force we've already seen is the density of the fluid now times the displaced fluid. So we have to use the immersed volume, not the total volume. Okay, this is a displaced fluid times gravity. All right, so from that we have the following. These are supposed to be equal. Air equals buoyant force, so that tells you this expression over here, density of the object times gravity equals the buoyant force, which is the density of the fluid, times immersed volume times gravity. Okay, so gravity cancels out. Now if you divide both sides by the density of the fluid, this goes away, and if you divide by V naught by V naught, this goes away, we get the following formula. The ratio of the density of the object, of the floating object, by the density of the fluid equals the ratio between the immersed volume and the total volume. This is equation of floating objects. Okay, the ratio between the densities equals the ratio between the immersed volume and the total volume. Okay, so this equation, if you know the density of the fluid, you can easily obtain the density of the object by just looking at the fraction of the object that is immersed in the object floats. Okay, now let's look at an example. We know density of water is 1,000 kilogram per meter cubed. Now it's known that ice floats in water. The density is 1,000 kilogram per meter cubed with 90% of its volume immersed. The question is calculate the density of ice. The density of ice. Okay, so we're told is this ratio over here, the ratio between the immersed and total is 90%. So what we're told is the ratio between the immersed ice and the total volume of the ice is 90% or 0.9. Okay, and of course we're told that the density of the fluid is 1,000 kilogram per meter cubed. Okay, so we're going to use the equation of floating objects, which is in this case the density of ice divided by the density of water equals 0.9. Okay, of course density of water is 1,000, so we've got density of ice equals 0.9 times 1,000. Okay, and that is 900 kilogram per meter cube. Okay, so from the fact that ice floats with 90% of its volume immersed, you can actually calculate its density. Okay, now so much about fluid statics. Now we're going to look at fluid dynamics. Fluid dynamics, this is the study of fluids in motion. This is study of fluids in motion. Fluids in motion. First we're going to look at a very simple relationship called the continuity equation. So let's look at the continuity equation. Continuity equation. Okay, let's consider a tip of different size, two tips of different size connect together. So let's say this is like this, and let's say we got fluid going this way. All right, and let's say the cross-sectional area over here is A1, and the cross-sectional area over here is A2. Okay, now what we can say is the amount of fluid that enters over here in a given time interval should be equal to the amount of fluid that leaves this cross-sectional area in the same time interval. In other words, the rate of flow should remain constant. Okay, the amount of fluid that enters this tube in a given time should be equal to the amount of fluid that leaves this one in a given time. Okay, in other words, the rate of flow should be a constant. The rate of flow is a constant. Okay, even though the size of the pipes is changing, the rate of flow will not change. So what it means is, let's say the amount of fluid that enters T1 is delta V1 in a given time interval. That equals the amount of fluid that leaves the other tube in a given time interval. Okay, but what is delta V1? Let's say this is the amount of fluid that enters in a given time interval. Let's call this delta X1, and let's say this is the amount of fluid that that leaves it in a time interval, and let's say delta x2. Okay, delta x1, delta x2. So this volume is this cross-sectional area times delta x1, and this volume is the cross-sectional area times the height delta x2. Okay, so we can say that but delta v1 equals a1 times delta x1, and delta v2 equals a2 delta x2. Okay, so that we have a1 delta x1 divided by delta t equals a2 delta x2 divided by delta t. But remember, this is distance divided by time. Okay, so it is the speed of the fluid in T1. Okay, but this ratio delta x1 over delta t is v1, which is, let's say, equals b1, which is speed of fluid in T1, fluid in T1, and then delta x2 times delta t, and this one over here, delta x2 divided by delta t equals v2, which is speed of fluid in T2, speed of fluid in T2. Okay, and so we get the following question. This is v1, this is v2, so we get the cross-sectional area a1 v1 equals a2 b2. Okay, so this is what we call the continuity equation. The product of the cross-sectional area and the speed of the fluid is a constant, right? Now let's look at an example. Let's say a tube of cross-sectional radius 2 centimeters is connected to a tube of cross-sectional radius 4 centimeters. Cross-sectional radius, let's say 4 centimeters. Now, if fluid enters T1, let's say with a speed of 4 meters per second, calculate its speed in tube 2. Okay, so we have these two tubes connected together, and we're told this radius over here, that's R1, is 2 centimeters, and this radius over here, R2, is 4 centimeters. Okay, and then we're told fluid entering this with the speed of 4 meters per second. So we have to calculate the speed of the fluid over here. That's V2. Okay, so the question is A1 B1 equals A2 B2, right? But this is a circular cross section, so A1 equals pi R1 squared and A2 equals pi R2 squared. Okay, so you've got pi R1 squared times speed in T1 equals pi R2 squared times speed V2. Okay, so pi goes away, so we're looking for V2. Okay, that's question mark over here. So we've got V2 equals R1 squared divided R2 squared times speed of the fluid in T1. Okay, So that is, if you want, you can relax this r1 over r2 squared v1. Okay, so that is r1 is 2, r2 is 4 squared times speed in t1 is 4. Okay, so this is 1/2 squared, that's 1 over 4 times 4, that is 1 meters per second. So the speed of the fluid in tube 2 would be 1 meters per second. All right. Next, we're going to look at Bernoulli's equation. Bernoulli's equation. Bernoulli's equation. This is basically conservation of energy for fluids. So let's proceed as follows. To make it more general, we're going to use tubes at different elevations so that we can include gravitational force. Let's say we get these two fluids at different elevations like this. Okay, let's say we're using this coordinate system, so this would be our y1, and this would be our y2 over here. Okay, the gravity. All right, so I'm going to use this coordinate system for y1 and y2. All right, so we're going to make use of the work kinetic energy theorem. If you remember, the work kinetic energy theorem implies net work done equals change in kinetic energy. Okay, so it's going to be our initial, the speed at t1 will be initial, the speed at t2 would be our final. It's going to be t1, it's going to be t2. Okay, so this is we're going to take a small mass delta m, so you're going to have delta m v2 squared minus half delta m v1 squared. Okay, so this is the, if you follow a small mass of the fluid, this would be its kinetic energy over here, and this would be its kinetic energy over here, and this would be its kinetic energy over here. All right, but what are the forces acting on this object? Of course, there are two kinds of forces. One is the force due to pressure difference. Okay, the reason it's moving this way is because you got pressure on this side, it's called P1, is bigger than the pressure on this side, it's called P2. Okay, so we have force due to pressure difference, and then of course we have gravity involved. Okay, so forces acting are gravity and force due to pressure difference. Force due to pressure difference. Okay, now work done by W net equals work done by gravity plus work done due to pressure difference. Okay, all right, now this is a conservative force. All right, so this can be the mass times gravity is the negative of the work done, which is you get y2 minus y1. Okay, that is the work done by gravity, the negative of change in potential energy. Okay, mgy2 minus mgy1 is the change in gravitational potential energy, and then of course the negative of that. How about the work due to pressure difference? Okay, so you get force P1, P2 over here, and the force is going to be the cross-sectional area A1 times P1, and it's going to be the pressure 2 times cross-sectional area P2. Okay, suppose this force is pushing by delta x1 over here, and then by delta x2 over here. Okay, so the work due to pressure difference, work due to pressure difference would be this force pushing to the right, which is the force P1 times A1. This is a force, and then times the distance traveled, delta x1. Okay, minus the force on this side, P2 times A2. This is the cross-sectional area A2, and this is the cross-sectional area A1. Okay, so you've got P2, A2, and then times the distance traveled, delta x2. Okay, but you see, A1 delta x1 and A2 delta x2 are the amount of fluid that enter in the same time interval, right? So, but A1 delta x1, that's the volume that enters T1, equals the volume that leaves tube 2, let's just call delta V. Okay, so we have P1, and then delta V, and then we got P2 delta V. Okay, so this work due to pressure difference, is P1 minus P2 times delta V. So what it means is the net work done is the work done by gravity, which is negative delta M times Y2 minus Y1, plus the work due to pressure difference, which is P1 minus P2 times delta V. All right, and that also equals to the change in kinetic energy, which is half delta M V2 squared minus half delta M V1 squared. Okay, so let's move this around. First, I'm going to divide the whole equation by delta M. There's gravity over here, I'm sorry. Let's divide the whole equation by delta V. So this implies that, you see, these two are equal. So we've got, if you divide by delta V, this becomes P1 minus P2. If you divide this by delta V, you give delta M over delta V times gravity times Y2 minus Y1. And then, of course, the other side becomes half delta M over delta V V2 squared minus half delta M V1 squared. But delta M by delta V is the density of the fluid. Okay, so we have the following equation: P1 minus P2, okay, and then minus the density times gravity Y2 minus Y1 equals half the density V squared minus half the density times B1 squared. Okay, now we're going to collect the ones on one side and the twos on the other side. So you've got P1 from here minus rho GY1 over here. Okay, and then we'll take the other side to the room positive. So this gives us P1 plus density times gravity times Y1 plus half density times V1 squared equals P2 density times gravity times Y2 plus half times density times P2 squared. This is what you call Bernoulli's equation. This is Bernoulli's equation. Now let's look at an example. Suppose, let's say we have this situation over here. Let's say this difference in elevation is, let's say maybe 10 centimeters. Okay, that is y2 minus y1 is 0.1 meters. Okay, let's say we're talking about water. The density is 1000 kilogram per meter cubed. Let's say the cross-sectional radius of this one is 4 centimeters. So you've got a radius of one is 4 centimeters. And let's say the cross-sectional radius over here is 2 centimeters. That's R2 is 2 centimeters. Let's say the pressure at T1, let's say it is maybe 20 kilopascal. Okay, and let's say fluid is entering this over here with a speed of 2 meters per second. That is V1 equals 2 meters per second. So the question is to calculate the pressure at T2. Okay, now first we need to calculate the speed at T2 because we need it in this equation, right? For that we're going to use the continuity equation, which is I1 V1 equals A2 V2. That is, these cross sections are circular, so it will be R1 squared V1 equals pi R2 squared and then V2. Okay, squared. So pi goes away. So you've got the speed V2 is R1 over R2 squared times V1. Okay, so the radiuses are R1 is 4, R1 is 4, R2 is 2. So you've got a square times V1, and that is 2 meters per second. Okay, so this is 2 squared 4, and that's going to be 8. Okay, so Vt is 8 meters per second. Okay, now we can apply the continuity equation, and that is P1 plus density times gravity times y1 plus half density times v1 squared equals P2 plus density times gravity times y2, and then plus half density times v2 squared. Okay, so we're looking for this one. So we just plug in the numbers. Now the elevation is 10 centimeters. You can put y1 at 0 and y2 at 0.1. Okay, if you put a coordinate system over here, we can say that y1 is 0 and y2 is 0.1. Okay, if you put the origin over here, so again is y1 equals 0 and y2 equals 0.1, or you can move this one over here and then you can use the difference 0.1. all right, so we've got P1 is 20 kilopascal, that is 2 times 10 to the power of 4 Pascal. We've got plus density 1000, well, we've set this to 0, and then plus half of density. V1 was 2 squared, that equals P2 plus density times gravity, and then y2 is 0.1. okay, and then plus half times density and then times the speed squared. Okay, so and then we solve for P2. This will go away, so we've got 20,000 plus 2,000, we've got times 10 to the power of 4. We have over here, I think 2,000 equals P2 plus this is 1, that's plus 1,000, and then 16 divided by 2 is 8, maybe plus 8,000, so on. And then we can solve P2 from here. This is that's 16 divided by 2 is 8,000, so we've got 8,000. So we have 22,000 over here, and then 1,000, 9,000. So that is 22,000 minus 9,000 is so we've got 22 minus 9 times 1,000 equals P2. That's 13. So we've got 13,000 Pascal, or you can say 13 kilopascal.